In my lab, for studying the motion of a falling object starting from rest, I chose to use a ball of paper with a mass of 0.0013 kilograms. After choosing a system to study, I decided to choose a broomstick with a length of 4 feet or 1.2192 meters to help calibrate the video data. You'll notice that the quality of the video is not great. The camera used in recording my experiment had an option to select the frame rate, with a trade-off of losing some picture quality. After recording my first attempt at 30 frames per second, I noticed that the motion of the object was extremely blurred and hard to determine the center of mass. This trade-off seemed worthwhile as the motion was captured more accurately and the unimportant information, such as the definition of my hand, was sacrificed. The first computational model I created only included the weight force as the total forces acting on the system. The constant g was set to the magnitude of Earth's gravity, which is 9.8 meters per second squared. This is the only force from the surroundings that was added into this model, so Fnet was set to the weight force W. The weight force W is defined as the ball's mass multiplied by the gravity multiplied by negative j hat. All arrows representing the drag force were removed from the calculations for this model. As I run this model, we can see that the ball's velocity starts slow at first and begins to speed up as the weight force's influence acts upon the object. This is depicted in this way because there is no opposing force to counteract the weight force, no push for gravity's pull. But this being a model based upon Newton's second law, all forces are not required to equalize. The yellow arrow shows us which direction the weight force is pulling on the ball. Graphing the model predictions with the experiment data, we can see that in the beginning stages of acceleration, the model does a fairly decent job in predicting the motion, but as time progresses, we see that there is obviously at least one other force involved in this object's motion, as the model says the ball should have traveled further in less time during the end of our observations. The second computational model created for this study of a falling object includes the turbulent drag as well as the weight force. The constant g remains the same as in the previous model, but more lines of code were added. For the drag force Fd, this equation tells the program to multiply the drag constant, which is dependent upon the object's surface area, by the square of the ball's velocity times j hat. To find out what a good estimate for the value of b is, I employed the use of trial and error until the model's prediction of the ball's final position was the same as the ball's actual final position. Through this process, I found that b is equal to 2.399 times 10 to the negative 4 Newton seconds per meter. In order to calculate the arrow scale to correctly display the magnitude and direction through the arrows, I multiplied the ball's mass by the Earth's gravitational constant to get the weight force in newtons. In this case, that was 0.01274 newtons. Then from there, to have an arrow that is 2 meters for every 0.01274 newtons, this would equal to 156.99 newtons per meter. Such is the value chosen for my arrow scale. Running this model, we can see that as gravity's pull increases the velocity of the ball, the blue arrow representing turbulent drag becomes visible, showing us that drag is counteracting gravity's pull. This would help explain why the first model's predictions were incorrect near the end. Graphing these predictions with the experiment data, we can see that this model did a much better job predicting the motion, though it does slightly overpredict between 0.15 and 0.3 seconds. This is most likely due to the fact that the value chosen for the constant b was close but not exact. Now looking at the graph with both model predictions and the experiment data, we can see that the model constructed without the drag force predicts the motion very well for the first 0.3 seconds, showing that within this time the drag force is negligible. But overall, the model that includes the weight force and turbulent drag does a much better job at predicting the motion of this object. With this graph, we can see that in the model predictions that do not include the drag force do not express terminal velocity being reached, as there is no opposing force to equal out gravity's pull, equalizing the speed in which the ball falls, so the ball will continue to speed up. The model with drag force, however, we can see that after about 0.45 seconds, the velocity does not increase, but rather starts to become constant. This would indicate that the weight force and the drag force are beginning to equal out, which would indicate that the object is reaching terminal velocity. If the ball was initially thrown towards the ground instead of being dropped from rest, then the drag force would come into play much sooner. This initial velocity would also make the weight force negligible until the drag force begins to slow the ball down to the ball's terminal velocity, effectively reversing the order in which the forces act upon the system. I have come to this conclusion by noticing that as the ball's velocity begins to increase, the drag force becomes more of a factor influencing that velocity. The velocity of the initial throw would null the pull on the ball by gravity, as this is only 0.01274 newtons, and gravity would not add to the velocity until the downward force was less than that.